Hello, everyone. So we've just been talking kind of about the plan for the next coming week, which of course you can find in the chapter overview. And the question on the table is there supposed to be an answer keeper following kinematics? No, there is not. There's not supposed to be one. As a matter of fact, I want you guys to get away from the necessity of an answer key. Now, I won't entirely forego them in the future, but there's going to be probably more assignments that are going to not have answer keys because you kind of have to be able to stand on this is what my answer is. And what I'll probably do is I'll post the answer key after the assignment is due. So then you can kind of look back to start to see like, okay, did I do this right? Didn't I? So you'll know eventually, but it just, there's a comfort level, of course, in having the answer key, but probably more importantly, the thing I worry about is people reverse engineering answers on answer key. Yeah, I know this answer is supposed to be this, so I guess I do. You should know how something works because of the definitions. We're going to spend a little bit of time here before we get going on today's particular thing, answering questions. So I've got a little bit of time here, so if you have questions potentially on the intermediate kinematics worksheet, I'm not going to fully go through problems, but if you're kind of confused on how to set up a problem or have no idea what a problem is asking, or weren't sure like how to finish part B on number 2 or number 6 or whatever it is, now is a perfect time to ask. But here's the deal. I'm not going to guess what your questions are. I probably know what they probably should be based on the amount of emails coming in, but I require you guys not to be passive on this. If you want to know, you ask. Otherwise, that's it. So we'll spend probably 10, 15 minutes on this, not a ton of time. But what questions do you potentially have over kinematics and problems we have done? Yes?
2B, it says that you started.
I assume you're on 2.4, yes?
Oh, yeah, sorry.
Okay, it's all right.
Yeah.
On part A, you found that the displacement was 31 and change, right?
Oh, yeah.
If I'm not mistaken. 31 point, I don't know, it doesn't matter. Okay, and then what does B say specifically? Oh, come on, Toby. There we go. Okay, if it started 23 meters from the light pole, where is it now considering the light pole? Okay, one thing I probably should have added, I should have definitely added this, and this would add to confusion, Lillian, the fact that it's moving away from the light pole as opposed to towards the light pole, because that is kind of a little bit confusing on how you set it up. But basically, all it says is this. If this is the light pole, and the light pole is 0, and your car is over here at the very beginning, what is 23 meters? You're given and find. What is 23 meters? You're starting. What's that? Have you traveled 23 meters? No. That is initial position. Initial position is 23 meters. Now you know from your calculations on part A that the object is about to travel 31.6 meters, or I don't know, it's 31 and something, I can't remember exactly. So the question on the table is, where does it end up? Now, somebody asked me yesterday, a good question, they said, is there an equation for this? And I said, yes. I mean, you can just recognize that it's just 23 plus 31.6, but here's the equation in a nutshell. It's the definition of displacement, or the definition of the change in anything. How do you get the change in anything? Final minus initial. And so if I want to know position final, add that on both sides, and there it is. What's the initial plus how much is the final? I'm sorry, how much has it changed equals the final. And that makes sense, right? If I have 3 jelly beans and someone hands me 6 jelly beans and my jelly beans have changed by 6, my initial was 3, my change was 6, the end should be 9. Now the reason I would argue, Lillian, that you would not want, because you put the car over here and said that this was 23 meters. Oops, 23 meters, dummy. Is this, you establish excuse me, you establish your direction. So when I said 23, that kind of says that is positive 23. And so in this particular case, if you said that way is positive, then this is not positive 23. That would be at negative 23. Does that make sense ish? I admit, by the way, and I'm going to go back and change it, that that problem could be worded a little bit differently to help you out with that. But that is kind of your clue to let you know that it should probably be positive 23. Other questions? Yes.
For 2.5 default
Uh huh.
okay. So
2.5, which number?
first one.
Okay.
Would it be set up as going up with velocity initial 7.6 meters per second, change in time, you up and that net, yet acceleration I had going up as positive, so negative gravity, and velocity final 0 meters per second, and then going down velocity initial 0 meters per second, acceleration negative gravity again, and
Well, to be fair to you, though, you don't need to go down here, right? There's no reason to go down. The problem doesn't ask anything about that. Part A asks how high it's going to go, right, which is entitled down the way up, and Part B asks how long it's going to take that maximum height. So you don't need to worry about anything down.
I was looking at part B for questions, so you're answering questions.
That'll certainly do it. Yep.
Thank you.
No, there's no problem. No problem. Also, a heads up on this particular problem as you're looking at it. Once again, it says, but falling kinematics is no different than everything you've been doing. You're just mostly going to be dealing with stuff going up and down. But to that end, all of the kind of the techniques that you learned already with intermediate stuff, with using quadratic equation at times versus how and when to split up your particular sets of variables, as well as in this particular case, the fact that this 0.8 meters, be careful with this because this will confuse you. Is this a displacement? No, this is not a displacement. If you put it in displacement, A, there's no way you're going to be able to cancel it correctly, but B, you're going to sit there confused for a very long time. So I go back to a lot of times students' confusion has nothing. We get very focused. Listen, I do kinematics, and we get very, very focused on using those 4 kinematic equations. We want to use them, right? And you get this gut feel like the big part of physics is when you got that equation, you're doing the algebra and you're plugging the numbers in and getting the answer. I want to be very clear. Yes, I want all that stuff to be good, but that is not where physics actually is. Physics is in the definitions, is understanding that the height is actually, that 0.8 is initial height. That does not belong in a displacement. It's using your imagination to think about what that situation is. Courtney, I'm really happy that you pointed this out because I do have a lot of people struggle with this towards the beginning. If I'm trying to go to the max height, it's recognizing that at the max height, velocity final of that is 0, so that I can put that in that particular spot. All right.
So for how high it will go, you add the 0.8 to whatever you get.
Exactly. And honestly, it's like literally what we just did, right? It's just, I mean, if you want to make it, you could do this instead. It's just, hey, there's your displacement if you want to say height, but I don't really need you to. Height final minus height initial, and once again, height initial plus however much it changes will give you height final. So of course you have to calculate the change in height, right? But you already have the initial, so just as you said, you add them together. Other questions? Yes.
So like these type of problems, like how do you like I just don't understand how like where you set your positive and like your zero.
Okay, well, 0 to a certain degree it doesn't matter. What we're finding is that it's important that you set them for changing your answer. Like in this particular case on this problem, I think you draw a picture, right? And I think when you draw a picture, it helps to go, okay, the object is leaving from here, so this would be my change in height, and this would be my height. From there, I'm probably going to go, hey, this is 0. I like the ground being 0. Now, whether or not which way is positive, both work fine. It's just that you're going to find that sometimes one is a little bit easier to understand versus one is a little bit easier to calculate. So like yesterday in the free fall lab, we set down as positive. And the reason why I did that is so that I can end with a positive G, and also so that my graph goes up into the first quadrant and not down into the 4th quadrant. And also, now how do I know all this? Experience, doing it the wrong way. I mean, ultimately, I think a lot of times students get freaked out because these problems take a while, and they go, "Well, I don't want to make any mistakes." If you're not planning on making any mistakes, then you're not planning on learning in here. And I think that you're going to get, you're going to sit in a spot and do nothing. There are problems in here. I'm sorry to tell you this. You will spend 5-10 minutes on a problem and get it wrong, and probably have to do it 2 or 3 more times before you actually start. But if you don't do that, there's no way to learn the problem. I wish there was. I wish there was a way to be like, hey, here's all of my experience, so you know all of them. I know what to do only because I've made the wrong mistakes, right? So that's ultimately it. Now, here's a generic way to do it, okay? A generic way that I like is if it's only going one direction, then make that direction positive, okay? Like if I have a car going to the right, I make it positive. Why worry about it, okay? If I have an object, so like in this case, I only have the ball going upward, so I like up being positive. Of course, that does make gravity negative in that case. If an object is going both up and down, especially on free fall, it's a good idea to just establish that up is positive, because you kind of have this natural intrinsic that up is positive, right? And down is negative, and that feels right. If you were to make down positive, that makes for some really weird answers. Like in this case, gravity is positive, great, but displacement is negative because it's going up, and that's going to go like, wait, up, negative. It's just going to make your brain short circuit a little bit in that front, which again, completely possible to do the math that way, but not super easy. Does that make sense?
Yes.
Cool. Any other questions? I am surprised, and I'm fine if you guys are all good with it. I don't need to go over it if you didn't. I'm surprised that nobody asked about 2.4 part, number 6 part B. Do we want that or no? Yes, no? Okay. 6B. Specifically, okay, curious, falls out of a 6-meter tree and is caught. Hopefully you saw the displacement there should be 5 and not 6, right? Because the height of the tree is 6. That is not saying how far he's going. And so you should get that he lands at a speed, he's caught when he's at a speed of 9.9 meters per second. Now, whether or not that's positive or negative depends on which direction you made which. This is one of those things where he only is going one direction, but I find it a little bit strange to make down positive here, because this means when the man in yellow catches him, his acceleration up should be negative if done correct. So that's a little bit weird to me. So I would probably make up positive here. If you didn't, it's fine, but you should end up with an acceleration of 16.5. I think that's what it is, right? 16.5 meters per second squared. Are we good with part A? Is there any part of that you want me to go over? Do you need me to do part B at all? Or are we fine? I said go. I heard go over it. A, B, both, neither. Just B? Both. Okay. So very, very quickly here, we have a tree. Okay. The first thing, the most important thing that you needed to recognize here is that there are 2 accelerations. Yes? If you don't recognize there's 2 accelerations ahead of time, you don't stand a chance of doing any part of this problem correctly, right? Do you see why there's 2 accelerations? Yes, no, we're good on that. We want me to discuss it. Sure. Okay. So, firstly, there's the acceleration of falling, right, caused by gravity, and the catch of the guy in yellow, the man in yellow, would be a different acceleration. How can I easily see that? Well, simply put, gravity's speeding him up, and the catch is slowing him down. Those have to be 2 separate accelerations. Even if they're the same number, they're 2 different accelerations. Does that make sense? And like we said, if there were 2 different accelerations, we rely on this assumption that acceleration is constant. Now we can change it, but it has to change from one to the other, and that means there's a different set of variables. So there should be a set of variables for the fall and for the catch. So we have 6 meters here. He starts up there. He's caught 1 meter above the ground. 1 meter's not that tall. Apparently, the man in the yellow is very short. I repositioned poorly here. There we are. Okay. So for the fall, you should have, I'm going to say ground is 0, up is positive. Initial velocity is 0, acceleration should be negative g, the fall should be negative 5 meters. 0.6 does not go in time. Okay? Why not? Well, because the problem very clearly dictates that that is 0.6, excuse me, he is caught in 0.6 seconds. Yes? This time here, and we don't know it yet, but what does this time here represent? How much time it took for him to fall. Now we can calculate it, but it's important that you recognize that and don't just go, oh, a time, put it in there, because obviously that's going to potentially screw you up. Also, as I mentioned yesterday, if you have 3 variables in a set, be wary of placing the 4th, because either it's been calculated or you're putting something in the wrong spot, and it's more than likely going to be that second one. Okay? Okay, so what do we know for the catch? What do we know for the catch?
The velocity initial is not quite.
Well, okay, we haven't got there yet. We're assuming we're at the beginning of the problem right now.
The velocity final and the velocity of the fall equals.
Velocity of the final should be 0, assuming he's caught, although actually that's not fully true, which we'll get to in just a minute. The time, 0.6 seconds. Right, and if you want to put that up here, you can kind of do something like draw an arrow or something to that particular effect. Yeah, whatever the speed is right here at the end of the acceleration of gravity will be the initial velocity, I said speed, not velocity, should be the initial velocity of the second section. Yes? We go with that? All right. So, come on, Debbie. Velocity final squared equals velocity initial squared plus 2a delta x. Vi is 0. Velocity final equals the square root of 2a delta x, which should be the square root of 2 times negative g times negative 5 meters. And when you get done, your calculator will spit out 9.9 meters per second, but you should recognize that's wrong because why is it negative?
Because of the square root.
Sorry, not mathematically why is it negative. Why in this situation should it be? You're right, 100% right. Why should it be negative in this situation? Because it's going down and we established up as positive. Had we established down as positive, then we would not put a negative on this. It would in fact be positive. Okay? Please note that this negative is not magic math. Every square root comes with plus or minus in front of it. This tells us the initial velocity over here. Once again, you can write that or you don't have to. But from here, we can find acceleration with this equation right here. Put the second part in different color here. I told you the other day, and this is true, you can always start with Vf equals Vi plus A delta T, but you can also, knowing that this is the definition of acceleration, go here. Now, here's what I notice a lot of people making the mistake on. They do correctly cancel this, but they go, oh, this is super easy. I'm just going to take negative 9.9 divided by 0.6, and you get a negative 16.5 meters per second squared. That is not correct. Why does it not make sense that Curious is traveling at negative 9.9 and then has a negative acceleration? What would that imply? Correct. That would imply that he's falling pretty fast, and Maniello didn't catch him. He grabbed him out of the air and shoved him even harder into the ground, speeding him up for that last meter. Okay, he definitely hits the ground in that case. But watch here. Here's what happens mathematically, which is important. This negative is from the equation, but within Vi is this negative. So we have negative of a negative, which of course correctly cancels as it should, to give us positive 16 meters, 0.5 meters per second squared. Questions, concerns there? All right. Next, part B. You don't have to do this, but it's probably advantageous in this particular time. I'm going to set up another set of variables here. The question on the table is now, does he hit the ground? Whenever a question is asked of you and we don't know the answer, okay, the first thing that you want to start off in your given is this. What two things up here are definitely going to be the case? We don't get to change them for this situation. What two numbers? So we're talking about while he is being caught. Would you stop it with him? I did this. What two numbers? We're looking at this section right here. The question is, does he in fact hit the ground? So what of those 5 variables is 100% the case? Definitely, definitely, definitely. Acceleration is positive 16 meters, 0.5 meters per second squared. No, not time. Velocity initial, correct. Should be negative 9.9 meters per second. So you got two things. Whenever you have a question, you now, excuse me, you now can ask a question by placing a third variable in there. What do I mean by that? Well, the first thing that I could do it either way, it really doesn't matter, is I could say, math, what if this was 0 at the very end? And what I could ask then is, how far will it need to travel? Because once 3 variables are set, the fourth is decided, meaning if I've got these 3 variables, this takes a very specific amount of displacement. And if this displacement is bigger than -1, does he hit the ground? Yes. He very much is going to hit the ground in that particular case. Yes? The other thing that you could do, by the way, the answer is yes, he does hit the ground. The other thing that you could do is you could say this. You could say displacement is -1 meter. In which case, what you could then do is ask, hey, how fast is he going after -1 meter? If there is a velocity at all, then yes, he's going to hit the ground. Does that make sense?
Why would time not be set with it?
Okay, so I'm recognizing as I'm standing up here that there's a little bit of a misgiving in this particular problem, that actually he does in fact hit the ground, which means it would not take 0.6 seconds. It would take less time than that. So this problem is a little bit kerfuzzled in that particular regard. And to your point, yeah, I could see you saying 0.6 seconds. That would fit with this set of variables here. Because obviously that's how you just solved for the first one a second ago. Same conversation though. You could go like, what's the displacement during that time? It is greater than -1, which means, quite frankly, he doesn't actually take 0.6 to stop him because he's going to slam into the ground in that particular period of time.
Will we have a problem with this on
100%. It's very likely that a question is not quite that wonky as far as the structure is concerned, but the question could be, this is also extraordinarily similar to a problem that most people did not struggle with, and that is, that I'm guessing, because I just didn't hear a lot about it, the plane landing on, does it land on the aircraft carrier? Now, the nice thing about number 4 is it sets it up for you. This is why people don't usually have this struggle, because they don't have to figure that out, and it basically just gives you 3 variables at the top and says, hey, go measure, sorry, no, it does, never mind, measure minimum time, and then can it land on 0.8 kilometers or 800 meters, and you have to go find displacement. So whenever it asks a question of can it, please understand that you really don't want to put that in your given because we don't know that that's actually the case. We're usually trying to solve for that variable to compare at the end. Questions, concerns? All right, any other questions? I want to give one more thing. I know it wasn't on this problem, but I did want to talk about it because it's particularly helpful with today's. Looking back quickly at the motion worksheet. Because I saw a handful of people like skip over it. Where'd it go? Number 11, okay, Cameron throwing one of Spainhour's mugs up in the air at 22 meters per second. How high did it go? This, of course, is utterly similar to just number 1 on the falling worksheet. And how long did it take before it hits the ground? You can decide to split up the variables. You don't have to split up variables, okay? Talking specifically about 11 here real quick. If Cameron throws something up in the air, like Spainhour's mug, okay, nailed it, up in the air at 22 meters per second from a height of 4 meters. That is a ridiculous height. Most human beings are around 1.5 to 2 meters, assuming they're not taller than 6 meters. So according to this, by the way, Cameron is currently 12 foot 4 inches, and that's where she's throwing the mug from. We're not even saying that's how tall she is. She'd be taller than that. So props. Anyway, but I'm not going to talk about the first half where it says how high does it go. That's actually a pretty basic problem. I'm going to talk about the second half and where it asks how long it takes. You can do this in one of 2 ways, and you should probably know both. The first way is split up the variables into 2 sets. Once on the way up, all up, and once on the way down. Oops. Now, is there a different acceleration in there? While the mug is in the air, does the acceleration change? No. The mug should have gravity the entire time it's in the air, yes? Which means you do not have to switch the variables. I told you that there are 3 reasons to split up the variables, okay? We've not gotten to the third yet. The first one is you can. You can split it up, like the window problem that we already went over. Like this problem. You could split up going up and going down, and that's fine. Okay? The second one I told you that you have to split up, like the problem we did on number 6 with the monkey, is when there are different accelerations. Are there different accelerations for this mug? No. So you do not have to split it up. But then students ask this question, how would I not split it up if I went the entire time? Well, the mug is going to do this. It's going to go up and come right back down. So the initial velocity, that should be easy. That should be 22 meters per second. I'm sorry, I'm assuming that the ground is 0 and up is positive. Acceleration is, of course, negative g. So what is the third variable that I could plug in here to be able to solve these problems? Well, do I know the velocity final? That would be the velocity right there. No, I don't. I have no idea how fast it's going at that time. Do I know how much time it's in the air? No, as a matter of fact, in part B, I'm pretty sure that's what we're here to try to go get. Do you know the displacement? The answer here is yes, and people struggle with this. Because what is the definition that we started with of displacement? The change in position. So you'll remember I said this, and it's weird to actually put it in the map. I drew a map up on the thing, and I said, hey, if you have an initial and a final, this dotted line right here would be the distance. This traveled space is the distance, but displacement is a straight arrow directly from where it starts to directly where it ends. So directly where it starts to directly where it ends, do we actually know the displacement there? What is it in this case? Almost negative 4 meters, because it is going down. Students struggle with that. They go, wait, Spanner, it definitely went further than 4 meters. Agreed, its distance was greater than 4 meters, but its displacement, its change in position, is negative 4. To which then somebody asks, okay, but isn't this going to confuse the math? No, the math knows it went up because you gave it this positive velocity here to begin with. It knows it's traveling up because of that. It knows it's pulling back down because of this, and it knows in total how far it'll have to go because of that guy right there. Questions, concerns? We got about 18 minutes left. I'm going to get you guys started on a problem. And the plan was in the second half of the day, we spent a little bit longer on questions, but I'm completely fine with that when that happens because that means I'm hopefully getting stuff that you need. I also put my own questions in there to be fair. Let's talk about the problem today. If we don't finish it in class, I would like it done for tomorrow morning. I'll walk around and check it off. Now, When I do this, it will be like an assignment a lot of times. I will grade it, and there's a one or done. It's a I have it completely done and tried, or nope, I didn't do it, I forgot about it, and there are no points. So please make sure that we don't forget this for tomorrow. Here is your problem. It's the Mojo Jojo Biojo problem. Mojo Jojo Biojo the clown tosses a tennis ball into the air. When it leaves his hand, it travels 2.5 meters until it gets to the max height. Now I want to be very careful here because we're going to be looking at the big sections. So if this is the tennis ball, here we go. Okay. This is the tennis ball. Okay, there's like going to be a few sections we're looking at here. So yes, when a person starts the tennis ball, they start down here probably at rest and then fling it. And notice that takes a displacement. Okay, so note carefully here that this 2.1 meters says specifically it's from the moment it left his hand until the very top. Yes? Okay. Then the ball took 0.43 seconds to leave Mojo Jojo Biojo's hand when he threw it from rest. So that's talking about this first section in here. Yes? Part A, how fast did the ball leave the clown's hand? Part B, what was the acceleration when the ball was in the clown's hand? And part C, how long did it take from when it left the hand to hit the ground? So again, be careful here. That time is referring to the moment it leaves from here, leaves from there, until it hits the ground. That's your problem. Work on this in a group. After you guys pretty sure you have the first answer or second, once you have an answer, call me over. I'll check. I'll be like, yep, you're good. Continue on so you know you're certain at least on the first parts. And then move on from there. Cool beans? Work on it kind of on your own, but if you get stuck or if you're not sure, work with your group. Video people, I'm going to leave you here. Of course, if you're coming tomorrow for a reason, please try to have this problem done, at least attempted. And obviously you can pause here to work on the video. Yeah, and if you want to know answers or you want me to check your work, again, email is the best bet. But I'm just going to stop the video here.